Hello, this is our presentation for the microbiology of vinegar. My name is Humberto Mesa.
I'm Charles Grant.
And I'm Gian Menjivar. All right.
So, the importance of vinegar, we have large quantities of acetic acid are used to make products like ink for textile printing, dyes, photographic chemicals, pesticides, pharmaceuticals, rubbers, and plastic. It's also used in some household products as a cleaner for like lime scale and removal of molds and bacteria and stuff like that. There's a world demand of about 6 million tons of acetic acid per year. In our day-to-day lives, we use vinegar to season and preserve food. Its acidic nature can kill most bacteria, or at least slow bacterial growth, depending on its strength and its pH level. So that helps us prevent other microbes from growing in these sources. As it is, microbes that produce acetic acid create environments that create makes it more difficult for other microbes to survive. That increases their fitness, so that increases their likelihood to reproduce and survive. The word vinegar comes from the Old French vinaigre, which means sour wine. Originally, its legends say that vinegar was originally discovered when forgotten wine was left in storage for several months, causing it to ferment and turn sour. Uh, Vinegar has been in books from since about 5000 BC, and we've actually found some vinegar from Egyptian urns from 3000 BC. So it's been around for a long period of time as well.
So the fermentation of vinegar is performed usually by the acidic acid bacteria, which comes from the genus Acetobacter, and it's also a gram-negative aerobic rod bacteria. And they're usually present in environments where alcohol is also present. The alcohol is produced by yeast from sugars, and then eventually the alcohol is then converted into the acetic acid. The process is dependent on how active the yeast and the acidic acid bacteria is. Temperature also plays a very big role on it. Uh, if the temperature is too high, then the yeast will start dying and the alcohol supply will lower. But if the temperature is too low, then the reaction to convert the alcohol into vinegar will take months.
All right. As for the mechanisms of vinegar production, we have to start with yeast fermentation. The yeast originally undergoes glycolysis, which is where we turn molecules such as glucose into 2-pyruvate molecules. This process also produces ATP, which the cell will use for energy. But the main important part here is the 2-pyruvate molecules. Using two NAD pluses and an adenosine diphosphate, we can turn it into two NADHs and adenosine triphosphate. NADH helps in the next stage of vinegar production, and ATP is just generally a piece of energy that we can use for more complicated steps in general cell processes. Each pyruvate molecule then loses a carbon dioxide molecule, which turns them into two acetaldehyde molecules. These two acetaldehyde molecules will then react with NADH in order to be further reduced into two ethanol molecules. This turns NADH back into NAD plus, allowing this process to be pretty consistently cycled in a cell, allowing for the constant change of pyruvate into ethanol in yeast. Then we have the acetic acid bacteria. Whereas the reduction of the concentration of pyruvate to turn into an increase of ethanol is a mainly anaerobic process. This process of turning it into acetic acid requires the presence of a lot of oxygen. So ethanol is transferred to an oxygen-rich medium that contains acetic acid bacteria. The ethanol is oxidized back into acetaldehyde using something called alcohol dehydrogenase. as well as using NAD plus to turn it into NADH. The acetaldehyde then reacts with the water in solution to form a hydrate, pictured here below. The hydrate then interacts with aldehyde dehydrogenase to form acetic acid. As stated before, all of this occurs in an oxygen-rich environment. So this step needs to occur separately from the production of ethanol. They cannot occur in the same environment because the conditions which are conducive to the creation of acetic acid from ethanol are not the same conditions which are conducive to creating ethanol from pyruvate. Finally, how can you make vinegar at home? If you wanted to go about this in a practical way, the first step, you need a source of sugar. This can be anything from fruits and juices to even some carbohydrates. You dilute the source in water, and then you add a source of yeast, and you wait about a week to ensure all of the sugar has been turned into ethanol. Alternatively, you could just skip the first two steps by just turning regular old alcohol into vinegar, such as wines and brandies. Then we dilute the resulting alcohol to have a desired alcohol concentration, usually between 5 to 9%, depending on your specific tastes. Then we take the alcohol and we heat it up to remove the presence of all microbes, including yeasts, because we don't want them to mess with the following steps. Next, we're going to add a source of acetic acid bacteria. This can be done by getting acetic acid bacteria on its own, or we can mix it with a small amount of unpasteurized vinegar called mother vinegar. This acts as a catalyst towards further creation of acetic acid. So this is the method that a lot of industrial producers of it use to create more vinegar. Then we ferment it over the course of about a couple months until the flavor has reached acceptable levels, usually around 4 to 5% the acidity of pure acetic acid. If you want to make your vinegar special, you can also do some interesting flavor substitutions. If you want something that's a bit more interesting, you could make balsamic vinegar, which is made from grape must, which is the pure essence of squeezed grapes. You could also make it from, as stated before, wines, apple ciders, and even rice and rice alcohols.
So there are a few limitations of this process. As we said before, natural environments such as at home production can take a few months to a year. Really depends on how much yeast you're using, how much sugar you're using, how much of the bacteria you're using. So in reality, only really about 10% of the world's acetic acid is produced biologically. It's much more efficient to use in industrial production, where you combine methanol and carbon dioxide with a metal catalyst, just significantly faster, significantly more products produced. Uh, However, for world purity, food purity laws, it requires a biological origin for use with food. So that's where you're going to get that 10% production of the vinegar. Usually you're going to be using a chemostat that can maintain optimal conditions for microbial growth, including the temperature, the pH, nutrient availability for efficient acetic acid production. One of the key things, again, is that if you're going to be doing this, aerating the process, because this is an aerobic process, will help increase the production, usually speeds it up so much that it's just so much more worth it to aerate the process. One of the main problems with this process, though, is that acetic acid is very corrosive, especially at high concentration, usually around 25%, can cause corrosive damage, can cause damage to skin, eyes, and lungs. And if you're using certain metals to carry out these, like to carry out certain metal vessels to carry out these procedures, it can corrode either copper, aluminum, iron, and zinc. So you need to make sure your process doesn't use those metals and that your process is actually efficient enough to produce the correct amounts of acetic acid for your needs. And so this is going to conclude our presentation on microbiology of vinegar.